Okay, in this case on the other side, you generally flow with inert gas molecules to maintain the low CO2 partial pressure. Now, these are prototypical, MOP structure, which I'm not going to go into detail, and people have also constructed the pure organic framework. That's what they call COFs, and also geolytic imide isolate frameworks, okay, which is basically MOPs, but the structures are similar to geolites. Okay, so that's why they call ZIPs. Again, the idea is these are all organic, inorganic hybrid sponge. Okay, but the pores are very well organized. Okay, and you take diffraction, then you will see huge nice peaks, which means these are crystals. Okay, three-dimensionally ordered crystalline hybrid sponge. Again, in this case, this window here is less than 5 angstrom. So as you might imagine, if you have like gas molecules, mixtures of gas molecules, okay, one is bigger than this window, and then one is smaller than the window. In principle, then you can separate based on size. Okay, this is called a molecular seeding. Okay, so why then stimuli responsive MOFs are exciting? Okay, again, this MOF in general are better than conventional solvents because you can now design and engineer. Okay, chemists love this material because now they can design, they can pre-design the ligands, and then they can expect, they can predict sort of a rough idea, rough structure of MOF that can be synthesized with the ligand that they have designed. Okay, so thousands of MOFs every year. Okay, thousands of MOFs, new MOFs are produced and reported. In particularly, stimuli responsive MOFs, okay, based on accessory kinetics, okay, that are not available with other framework materials such as geolites are exciting. Okay, let me give you an example here. Okay, this is again so-called the MEMS that Professor Zhu's group has synthesized. I'll talk more about this in a minute though. What this graph is, on the y-axis we have effective opening of the pore size, and x-axis is temperature. Okay, in Kelvin. As you can see here, as you start increasing temperature, then the effective pore opening start increasing. Okay, has a linear relationship. Okay, by simply changing the temperature. Now, imagine that you are absorbing CO2 and nitrogen, okay, onto this material, these MOFs. Now, or stimuli responsive MOFs in general. Okay, so this is CO2 before absorption. This is energy versus reaction coordinate. This is CO2 before absorbing. Obviously, this is in gas phase, correct? Gas molecules in solid phase will have low energy. That's why gas molecules want to sit on the surface of the solid as compared to in liquid, in gas phase, correct? So there is a driving force. However, in order for that process to happen, you always have to go through this activation energy. Okay, you pay some penalty, and you gain a lot. Nitrogen also will do same thing. Okay, so you have a slight advantage. Okay, because in this case, the energy that you gain for CO2 to be absorbed is slightly greater than nitrogen, which means CO2 will be preferentially absorbed. Now imagine if you apply stimuli, and by applying stimuli, you can actually increase the activation barrier for nitrogen a lot greater than for CO2. Then nitrogen cannot go over this activation barrier to be absorbed on the surface as compared to CO2. Obviously, CO2 as well, we have slight increase, okay, in activation barrier, but not as much. Okay, so now in principle we can achieve a very high CO2 selectivity because now we basically change the pore size in this case. Okay? And then after you absorb CO2, okay, and then you reverse stimuli, what happens is that now there is no activation barrier or very little activation barrier, right? which means you only have to provide this much of energy as compared to this much of energy in order to liberate CO2 from the surface to the gas phase. Okay, so this is exciting. So that's why we got this funding. Again, like I said, this is MEMS. That's what they call mesh adjustable molecular sieves. These are layered structure, and they are claiming that they have this gate over here, and they have space in between. Now, in order to access, okay, for the gas molecule to go to this space, they have to go through gate. Now, these gates can be selectively adjustable depending on the temperature. Okay, so 2.9 angstrom to 5 angstrom. Here, they have shown that this is possible based on gas adsorption measurement at different temperature. Okay, however, the problem is still, I don't know whether you have recognized this, the temperature is too low. Okay, this is Kelvin. Okay, so room temperature is right over here. Okay, 46 is right over here. Okay, so this is not going to be useful as they are now. And my colleague is developing a new type of, that's what they call second and third generation MEMS. First generation is already reported, okay, temperature is too low, as I said. Second generation is based on the hydrogen bonding and pi stacking interaction, and third generation is based on the base pair chemical group interaction. And we are still working on it, but it's not that easy to synthesizing MOBs are not that problem, but expect to getting the desired properties that we expected is kind of challenging. We're working on it. So the other idea that they have, Professor Jeong has, is basically the first generation MOB is basically MEMS is graphite structure, okay, layered structure. If you roll this graphite, okay, to make a ball, then that's fluorine. Okay, the same idea. They take this layer. If they roll it up, then you will have this so-called molecular porous metal organic polyhedra (MOP). Okay. So these are molecule, individual molecule. Okay. So they have synthesized it, and they have different generations of this structure. By the way, this yellow ball is not really there. Okay, this is only to illustrate that we have this much of space, cavity, okay, inside. Okay. So again, gas molecule will go through this window. So what is important is the size of the window, as well as what kind of functional groups inside the cavity. Okay. If the functional groups that we have in the cavity are somehow preferentially interacting with the carbon dioxide, then carbon dioxide will go into and nitrogen 1. So they have studied gas adsorption properties, in this case CO2 and methane. They have reported we do have some CO2 selectivity, but CO2 nitrogen, not that much. So we kind of moved on. Okay? And then the other MOF, stimulus responsive MOFs that Professor Su's group has been working on is optically responsive MOFs. So the idea is you have this functional group, okay, where depending on the stimuli, in this case UV, then if you apply UV, then this is called cis trans structure. Trans becomes cis. Okay, so I don't know whether you remember this, isomerization reaction, but this happens. Believe me. So by introducing these functional groups, okay, they can go through a cis and trans interaction depending on light and temperature. Then you can actually modulate, not only modulate for size, but also modulate the sites where the gas molecule can get access to. Okay, so again, this is the actual material that they have synthesized, and this is great illustration here. So CO2 and N2, CO2 in this case is adsorbed. If you apply UV, then this will go through the reaction that I have just shown you, go like this. Okay, then what happens is that CO2 is strongly interacting with this metal sites, and now these metal sites are no longer accessible by the CO2. So CO2 absorption capacity will decrease, which means CO2 has to be released, dissolved. Okay, so this is basically CO2 uptake as a function of pressure, and as you expose UV, what happens is that this functional groups will start to become this state, and then the CO2 uptake is gradually decreasing. Again, if you start increasing temperature, then you basically recover the CO2 uptake that you have originally had. Okay? So again, the problem with this material is that the CO2 uptake is still very low, and as you might imagine, this process is kind of long. Okay, it takes time. It's not like a instantaneous switch. So that's something that we have to work on, but in principle, it's interesting, exciting idea. The other material that we've been working on is PPN, porous polymer network. Okay, now nice thing about this material is all polymer. Okay, as with the cups, and because of that, the materials are kinetically more stable, and it has high surface area. Okay? As you can see here, for instance, nitrogen uptake, right? PET surface area is about 4,000 square meter per gram. Now, 4,000 square meter per gram, it's hard to imagine, right? If you have a gram of this material, that's corresponding to the surface area of Kyle field. Okay, 1 gram of material, because of the fact that you have a lot of internal pores. Okay, imagine yourself that you can actually expose all the internal surface to the external surface, externally. Then, if you have 1 gram of this material, then you have like Kyle field. You have like surface area corresponding to the Kyle field. Okay, so it's exciting. So we have tested CO2N2, and it turns out that CO2N2 selectivity is very good, about 100. And the CO2 uptake is also 38%, which is very good actually. It's not the best, but it's among the best porous material for CO2 capture. Okay. So we are excited about this idea. This idea. So now let me move on to talk a little bit about the membranes then. Okay. So if you have MEMS membranes, okay. So in general, let's say stimuli responsive membranes. Why these membranes are special? Okay. So first of all, here I have a gas molecules, okay, as a function of size. Imagine the gas molecule as a soccer ball or golf ball, whatever. That means helium is golf ball, and then isobutane is like baseball. Okay. So then you have all in between you have these different gas molecules. Different size. Now, if you want to separate, for instance, CO2 and nitrogen, okay, then you can simply adjust mesh size by changing the temperature. Okay, and then, which means high resolution separation is possible, and then somehow suddenly market shift. So nobody cares about separating CO2 from nitrogen.